Hello and welcome to this lecture from the Ada Core University course on the basic concepts of concurrency in Ada. This lecture covers the main Ada features that are used for programming concurrent applications. It assumes that you are familiar with the sequential programming features that have been covered so far, but does not require any previous experience with concurrency. After completing this lecture, you will understand the issues that are associated with concurrent programming and will know how to use Ada to solve these problems. Together we shall go through a series of slides and then you will be assessed on your learning using some quiz questions. Let's start by covering some basic terminology. A sequential program has a single thread of control, and you can imagine an execution engine proceeding one statement at a time, keeping track of its location and maintaining a stack to store local data and formal parameters as blocks are entered and exited and subprograms are invoked and returned. A concurrent program may have multiple threads of control. In Ada, the program unit that can have its own thread of control, that is an active program unit, is known as a task. In a typical scenario, multiple tasks need to interact with each other, either directly or through shared resources. Each task has its own stack, since it can call subprograms and execute blocks of declarations. A critical issue in concurrent programming is how to allow multiple tasks to access, that is read or write, shared data. The programming solution needs to be safe, preventing one task from writing to an object while some other task is accessing it. But it also needs to be efficient, and the syntax should be easily understandable. We'll see Ada's approach to these issues later in this module, and also look at how mutual exclusion may be implemented. For example, in simple circumstances, the hardware might provide the protection. Other solutions involve operating system or kernel mechanisms, or just careful program logic. Tasks sometimes need to synchronize their execution, so that one task is suspended until some other task signals an event that allows the first task to be resumed. There are various flavors for such events, and we'll look at some of them again later in this module. Before going into the details of the Ada tasking model, let's take a broader look and ask why. What are some of the reasons that you might want to use concurrent programming? Perhaps an obvious answer is efficiency. If your program is running on a multiprocessor or multi-core machine, you would like to take advantage of the processing power. But even on a uniprocessor, a program structured as concurrent tasks can have some advantages. For example, one task could be waiting for an I/O operation to complete, while another task performs the computation. Finally, the concurrency may be a natural part of the design. In a typical real-time program, there are various devices that need to be monitored or controlled, and the clearest way to express this in the program is through concurrent tasks. This diagram reflects the relationship amongst the various components of a concurrent program. Task 1 and Task 2 access some shared object or resource. The bidirectional arrow indicates that each task both reads and writes to the shared object. The lock indicates that there needs to be protection against simultaneous access from both tasks. Task 3 signals an event to Task 2. For example, perhaps Task 2 should only read from the object when Task 3 indicates that the object has a new value. As we mentioned earlier, a programming language with concurrent support should express these sort of interactions in a safe, efficient and understandable way. Each task is shown with its own stack. When a task calls a subprogram, the formal parameters and local variables of that subprogram are pushed onto that task stack. When the subprogram returns, those data objects are popped off of the stack. Note that if the same subprogram is called from multiple tasks, a separate copy of its formal parameters and local variables will be pushed onto each task's stack. This property is known as reentrancy, and in Ada, all subprograms are reentrant. To emphasize a point that we made earlier, concurrency may be either actual or virtual depending on the execution environment. We'll use the term parallel to refer to actual concurrency. Virtual concurrency means that the execution of multiple tasks will be multiplexed on a single processor, normally under the control of a task dispatcher that is implemented by a runtime library, provided by the Ada compiler vendor, and which in turn may rely on the services of an underlying operating system or kernel. The task dispatcher decides which task is to run based on the task's priorities, which can be controlled by the programmer in conjunction with the dispatching policy. For example, one common policy is run until blocked or preempted. That is, a task will continue to run until it either cannot proceed, for example it may need to wait for some event, or a higher priority task becomes eligible for execution. Another common policy is time slicing, which ensures that low priority tasks do not get starved for execution time. As we will see later, some policies are more appropriate than others for real-time systems where the meeting of deadlines needs to be ensured. The language provides a facility for the programmer to specify the dispatching policy. In the absence of such an explicit specification, the policy is not specified. The details may indeed depend on proprietary features of an underlying operating system. Different tasks can access shared data, but since the tasks and the data are part of the same program, a common address space is assumed. Ada also has facilities for dealing with programs consisting of multiple partitions that do not share an address space. These are described in the Distributed Systems Annex and are outside the scope of this current lecture. Ada language semantics do not dictate whether the concurrency is actual or virtual, and the same tasking program can be run in either environment. The program's effect may depend on whether there is actual concurrency and of course on the task dispatching policy. Let's now take a look at a simple tasking program which will illustrate some of the basic elements of the Ada model. The first thing to note is that syntactically a task looks very similar to a procedure. It is declared with a specification. Here it is simply the task name, but we'll see more general examples later, and then it's followed by a body. The specification is the interface to the rest of the program, and the body is its implementation, which can contain declarations and statements. So the question is, when do these statements get executed? In Ada, the separate thread of control that executes the task body comes into existence when the enclosing unit reaches the begin. At that point, one thread of control executes the statements following the begin of the enclosing unit, and the new thread of control executes the statements in the task body. Recall that these may be executing with actual parallelism or multiplexed under the control of a task dispatcher. For this example, let's assume we have actual parallelism. The enclosing procedure body simply contains the null statement, so it will execute and complete quickly. The task is a little more complicated, and it will execute a loop 60 times, and at each iteration it will display the string hello, and then suspend its execution for 1 second. Actually, the suspension will be for at least 1 second, so the task is not periodic. It will exhibit continued drift. We will see later how to obtain periodic behavior. Eventually, the task finishes its loop, and it too is completed. Although fairly simple, this example does illustrate an important point. After the enclosing procedure completes its execution, can it be terminated and its resources, such as its stack, be reclaimed? The answer in this case is no. The local variable n is on the stack of the thread of control executing the simple tasking program procedure. This variable is referenced by the for loop in the task. If the stack were reclaimed, then n would no longer exist, and the task will be referencing a memory location that may be in use for some other purpose. Such a situation is called a dangling reference, and would be a nasty bug to try to track down. To make sure that this cannot occur, the Ada rules require that a scope in which a local task is declared cannot exit until its local tasks have all terminated. In our example, execution of the simple tasking program procedure will be suspended at its end until simple task has terminated. Let's have a closer look at the structure of a task. First, a task in Ada is a construct that is declared, and in that sense is syntactically like other program units such as subprograms and packages. A task always consists of a specification, which may be empty as it is here, and a body. The declaration may be local to a subprogram body, block statement, or even another task body, and it can also be in a top-level package, in which case the task specification would go in the package spec, and the task body would go in the package body. The task body is the algorithm that will be performed by the thread of control that executes the task. It may contain declarations and also has a statement part. So when does a task start and when does it finish? This slide deals with task startup, known as activation, and the next slide will cover termination issues. Let's first look at the case where a task is declared locally, for example in a subprogram. The task is activated when control reaches the begin of the enclosing scope. At this point, the execution of the closing scope is suspended and the declarative part of the task body is elaborated. In this example, there are no declarations in the task body, so this initial step is completed immediately. Now the enclosing scope and the task body are each at their begin, and both are made eligible for execution. The task body and the statement sequence in the enclosing scope can execute concurrently, with the standard effect, either with actual parallelism or multiplexed under the control of a task dispatcher on a single processor. Now let us turn our attention to task termination. There is no explicit return or exit from a task. It completes its execution when control reaches the end of its body. If the task does not contain any inner task declarations, it is now okay to terminate. Termination means that its systems resources, for example its stack, can be reclaimed by the runtime support software for task management. An important semantic point is that the scope in which the task is declared cannot complete until the task, in fact all such nested tasks, terminate themselves. So execution will be suspended at the end of the enclosing scope until these dependent tasks have all terminated. As mentioned earlier, this rule prevents a potential dangling reference. If the enclosing scope could complete while one of its dependent tasks was still running, then such a task could reference local data in the enclosing scope after the stack containing that data item had been popped. That sort of bug is extremely difficult to detect, and fortunately, the Ada rules prevent it. Tasks are not necessarily declared in local scopes. Often the tasks are declared in top-level packages, also known as library-level packages, and in some applications this will always be the case. In such situations, a different set of rules for task activation and termination apply. Activation will occur just after the main procedure is invoked, and since the tasks do not depend on the main procedure, they can continue to execute even after the main procedure has returned. These rules match the Ada conceptual model of program execution. A program typically consists of a set of top-level packages and subprograms, and you can imagine that all of these are declared within the declarative part of the body of a so-called environment task. Just after the begin of the environment task body, the main procedure is invoked. So when the environment task reaches its begin, all of the tasks in the top-level packages are activated. When the main procedure is invoked, it executes concurrently with all of these tasks. These tasks do not depend on the main procedure, and thus the main procedure may return while these tasks are still running. This kind of situation is common in applications such as process control, where the main procedure performs some initialization and the library-level tasks are written as infinite loops. In this example, the procedure simple synchronization declares a couple of variables that will be assigned by the local tasks T1 and T2. The body of the procedure needs to reference these variables, but how can we ensure that the references only occur after the tasks have performed their assignment? In a later lesson, we will see how to accomplish this with a specific language feature that is designed to serve this purpose. But we can also achieve the desired effect by making sure that the references to the data objects only occur after the two tasks have terminated. Thus, we introduce a local block in the body of the procedure and declare the two tasks inside the block. When control reaches the end of the block, execution will be suspended till the tasks have terminated. The simple underscore synchronization procedure can safely reference the variables in statements following the inner block. Up until now, we have been ignoring the issue of exceptions that are erased inside a task. So let's now look at how this works. There are two contexts in a task where an exception may be raised. One is with the statements of the task body. A task body can have exception handlers, so it can anticipate abnormal behavior and take appropriate action. In such a case, when the handler completes, the task will terminate normally. What if an exception is raised in the statements of a task body and there is no handler? If this were a procedure and not a task, the effect is to propagate the exception back to the caller. However, such a rule is not appropriate for a task. Recall that the task will be executing concurrently with the statements of the scope in which it is declared. If the exception were propagated back to this scope, it would be an asynchronous exception, and it would be very difficult to program an appropriate handler to anticipate such a situation. As a historical note, asynchronous exceptions were once considered for inclusion in the original version of the Ada language, but were rejected because the language design team did not feel that such a feature could be easily reliable. Okay, so if the exception is not propagated from the task, what happens? Two possible alternatives. 1. Terminate the entire program, and 2. Terminate the guilty task but do not propagate any exception. In Ada, the second alternative was adopted. If the statements in a task raise an exception that is not handled by the task will be terminated silently. Such a situation is generally an error, and the program should be written either to ensure that this can never occur, or with appropriate recovery mechanisms to deal with a degraded configuration. These topics will be covered further in a later lesson. Declarations in Ada can also contain dynamically evaluated expressions, so it is possible for the declarative part of a task body to erase an exception when the task is activated. So what happens then? An exception raised in a declarative part is never handled by a handler in the exception part of the same construct, so it cannot be handled by the task itself. It would have been possible for the language design to take the same approach here as with exceptions raised in a task statement, that is, to simply have the task terminate with no propagation of the exception. But in this case, the propagation would not be asynchronous. That is, the declarative part of a task body is elaborated as part of the task activation, but with execution of the enclosing scope suspended. So there is no semantic problem to propagate an exception back to that scope, where it can be handled, and indeed that is the Ada semantics. The exception that is propagated back of such an activation failure is tasking error. So to recap, an exception raised in the statement part of a task body and not handled there causes the task to be terminated silently. The exception is not propagated. An exception raised in the declarative part of a task body causes the task to terminate, and the tasking error exception is propagated back to the enclosing scope, thus giving that context an opportunity to recover from the failure. Here is an example that illustrates some of these rules. If T1 raises an exception during the execution of its statement part and does not handle the exception, then it terminates with no notification to the surrounding procedure. If T2 raises an exception during the execution of its statement part, then this execution will be handled by the other's handler. This is a common style, allowing the task to perform some appropriate action, such as logging information to a file before terminating. If T3 raises an exception in its declarative part during its activation, then it will be terminated and the tasking error exception will be propagated. It will then be handled by the handler in the enclosing procedure. This lesson introduced the Ada tasking model. It explained that tasks are syntactically like subprograms and packages, consisting of a specification and a body. In that sense, a task is a module, that is, a design unit that corresponds to a concurrent activity in the problem space. Tasks can reference data from outer scopes, but as we will see later, this needs to be done carefully when more than one task is accessing the same object. A task is declared, but it does not come into existence as a concurrent entity until its enclosing scope reaches the begin. At that point, it is activated, while execution of the enclosing scope is suspended. Activation consists of the elaboration of the declarative part of the task's body. If no exceptions are raised during activation, the enclosing scope is awakened and the task can execute concurrently with the statements in the enclosing scope. If an exception is raised during activation, then the task terminates and tasking error is raised after the begin of the enclosing scope. Since a task and its enclosing scope may execute concurrently, the enclosing scope may complete while the task is still running. Execution of the enclosing scope will be suspended before it terminates. This ensures that data that might be accessed by the running task will still exist. Tasks may be declared locally, in subprograms, blocks, and in other tasks, but more commonly they are declared in library-level packages. In that case, they are activated just before the main procedure is invoked, and they can continue execution even after the main procedure has returned. If an exception is raised in the statement part of a task body and not handled by the task will terminate and the exception will not be propagated. This avoids the complexity and error proneness of asynchronous exceptions. We've now reached the end of the slides section of this lecture. You should now have enough knowledge of this subject to complete a small quiz with questions designed to test your understanding. Each question is marked and you will have a chance to review your score at the end of the lecture. Good luck. Here is the correct answer. Click anywhere on the slide to continue to the next quiz question. Here is the correct answer. Click anywhere on the slide to continue to the next quiz question. Here is the correct answer. Click anywhere on the slide to continue to the next quiz question. Here is the correct answer. Click anywhere on the slide to continue to the next quiz question. Here is the correct answer. Click anywhere on the slide to continue to the next quiz question. Here is the correct answer. Click anywhere on the slide to continue to the next quiz question. Here is the correct answer. Click anywhere on the slide to continue to the next quiz question. Here is the correct answer. Click anywhere on the slide to continue to the next quiz question. Here is the correct answer. Click anywhere on the slide to continue to the next quiz question. Here is the correct answer. Click anywhere on the slide to continue to the next quiz question. Thank you for attending this lecture from the Ada Core University. I hope you have found it a valuable step in learning the Ada programming language, and that you continue on to complete lectures from all the available courses. Thank you.